Okay, good afternoon, everybody. And my name is Goman Ho. And actually, this paper, I have other two co-authors, is Dr. Peng Liu and also Dr. Michael Liu. But I'm going to do this presentation. And I think my first couple of slides is very similar to Mr. So. And but I'll talk a little bit a little background before I do my research degree. And I was working in a CAD/CAM company doing computer aided design, computer aided manufacturing, and also computer aided engineering, which is in late 80s. And this gave me a very good experience in understanding not just structural engineering, but a lot of things and how to make our daily products, etc. And also now, I think most of us may probably have we are holding a smartphone. And currently, the CPU in a smartphone is very, very fast, right? And which is much faster and cheaper than recently there is a value come out and saying that the CPU in our iPhone, right, is far faster than a 1985 supercomputer by Cray. At that time, you're talking about millions of dollars for a supercomputer, right? But now, I think most of us, maybe half of us, are now holding an iPhone which is faster than that supercomputer. And because of all these changes, technologies, and so forth and so on, our working sequence, our working procedure change. And also with that, in the past, a hand drawing become a CAD drawing, which is probably in early 80s, right? We have a PC more popular and computer getting more powerful, and then we start to have a 2D CAD drawing. And after that, in probably and the time goes, and we have from 2D CAD drawing to 3D CAD drawing, and we can describe a object by a wireframe, or at that time we do have what we call the solid modeling, right? And this is by around like 2005. And besides that, in probably also with the contemporary architecture, right, we are no longer fixed on a structure with a regular grid line, right, similar to what Mr. So demonstrated. I mean, with the structure, we probably cannot have a grid line to define the structure. We work out very hard for the burst net. We have defined a grid line, but for water cube, you can call we have, but actually no. And the structure, the drawing, all the drawing, you cut a floor plane, right? You cut the section, showing the column. Actually, yes, we can give them a three-dimensional coordinate to define the column location, right? But actually, what does it mean to the contractor or the labor on site, right? Now, so, well, yes, it's difficult in order to do the structure, but at the same time, this is the development, and we have used, in order to create this iconic structure, we cannot just base on a simple 3D CAD drawing. It's still a CAD drawing, but it's a different meaning of it. And I was also involved in 1994. I was also transferred to our office in Detroit, and not doing structure. I'm doing car, and doing a car crash readiness analysis, right, for safety analysis and so on. And we use different kind of software for that, and because all the car and so on are like a little bit of, not a free form, right, but not a straight line, definitely. And so we have lots of software. We know a lot of software, and one of them is called CATIA. CATIA is very powerful software, right, developed by an airplane company, Boeing, and doing a lot of stuff. And also we can use this CATIA to generate a surface, right, a volume, right, either by wireframe. And also the point is for like burst net, we work with the architect on how to cut the plane, how to make the main structure, how to make the secondary structure. But one point is what the architect looking for is the bird's nest, right, is look like this. And for every line we cut, we have a box. And the box has to follow the surface. So it means the box is in the, when it turn the corner, it will be by curvature. A square in a bicurvature. Looks like a bit twist and bend, right? So what we did is we used criteria, and we draw the line, and then not the center line, but the surface line on the surface. And then we use criteria function to actually locate the box, and then follow the exterior line to generate the 3D geometry. But at the same time, we use this outer surface line and then offset it to become the structural center line to create our structural model. Well, it looks a little bit complicated, but this is what we do. Now, BIM. For the bird's nest, we use criteria to basically for the geometry and also for the and then we extract the data for structural analysis. And then later on, I mean, but 2005, I mean, we have something. We do have a BIM, but it's not very popular, and at that time, the BIM system is not very stable. But later on, I mean, again, maybe with the technology, computer, CPU, and so forth, right, we have BIM become more popular. This is Granny, and his process say BIM is the process of generating and managing the building information. Right? There's a lot of information in that model. A lot of information besides the maybe we call it the architectural geometry. We could have the lighting, we have the ceiling, we can have whatever we want to put in, right? And there's a lot of information so that all the party in this industry, mechanical engineer, facade engineer, maybe interior architect, you know, can work together and facilitate our communication. Right. Now, this is a structure. This is a project we work with CTBUH. It's in Ningbo, and we use this as one of our early attempts on working with architect, right, with the BIM system. And this is the architectural model. With the architectural model, we work out the BIM model. And so that our mechanical engineer could work with us and communicate with the architect. And then from that, I'm a structural engineer. And what we need is to convert this one into a structural analysis model so we can do the wind load calculation, the earthquake calculation, the gravity, etc., etc. And this is quite a tedious, labor-intensive process because maybe after a week, and we got an email from the architect, and then we have to redo this process again because the grid line changes so forth, so on, right? Unless they can change the BIM model directly. Now, but at the same time, say for this one shows the structural analysis model in a 3 dimension. We show it on the plan, and this is the BIM model, and this is the CAD drawing. Now, the process is we'll get the BIM model, but we still need to convert it into a standard 2D CAD drawing so that for contractor know or the contractor or everyone can work on the 2D, right, at that time, right? But you can see a lot of different, they are different models. They're not 100% compatible, right? There's a lot of issue like in the corner, right, in the corner, and how we can accurate in the BIM model, and the BIM model may or may not be able to generate the exactly 2D drawing or exactly the drawing that we are looking for. Now, again, I work in Detroit, and we have this cast reference study, and this very complicated computer model with all the components in a car, a dummy in a car, a seatbelt in a car, airbag in a car, right? And every time, I mean, we need to do it, and then we say, well, whether this is a male dummy or this is a female dummy, and what kind of airbag we need to put it in, then we have all this module changing, right? But it's easy because we define it as an object for like the tie. We can change the tie to 70-inch, whatever, 19-inch, 20-inch, whatever tie you want. You get the result and then do the simulation. Quite easy because we put it as an object, including like the airbag, the dummy, and so forth and so on. So how we can do it? And then we back to my early development in parametric modeling. Is parametric modeling start with probably in again late 80s. Is firstly applied in most common is injection mold. What is it? Is plastic injection mold. We have a die A and a die B, right? Or sometimes we call it punch or whatever. And then we have the plastic inside. And the designer, what we need is design the product. And the computer, the software will help you to design the die A and the die B. So once we have decided the product, what we want, then it will automatically generate the die. And then we can put a metal in a machine, the NC machine, and do the mold for you. Right? This is why we developed the parametric technology. And back to building industry. Oops, sorry. Back to building industry. Similar idea we can have that, right? But we only use it in probably like in the past 5 years, right? In parametric technology. We can say this is, assuming this is a form of a building, a tall building, for this conference especially, right? How taper, whether it's vertical or taper, what is the dimension, right? How we can going to change it, and we can dimension it, right? And we can define a geometry by means of lots of collector or information, variable, and so forth, right? So then all put it in a database, right? It could have, and then we can use it to with other software like Vinyls, right? With this one is Vinyl plus Grasshopper. We can define the floor, the bracing, the column, right? This is the information we can create. With this, then we can easily manipulate about, say, for this example, a building, right, which is not straight taper and which is not vertically straight. And we can see the difference is, say, if we have this pattern. And what happens if we change the width in the middle? Or what happens if we change the top dimension? And all the member size, all the member coordinate will be regenerate, right? And so that we can have a new model, we can do whatever we want. Similarly, we extract the corner at the top, make the circle, whether the corner need to be dimension, the radius, whatever, and we can see how the structure or the dimension will form, and then we can obtain the data. Right? This will help us to improve our productivity by also making a lot of options, right? And to save our time. Now, besides that, we can also define, well-define the part, and this is what a BIM model cannot do for us. We can define the various parts of the structure, say the mega column, the mega braces, the transfer trusses, the core, the beam, and the slab, and other whatever you want to define. As a horizontal system, vertical system, the lateral system, right? And so that we can put it and make all to be related. For example, this is an example we saw, the bracing pattern, how to connect it, right? You can change it very easily. Right? What we need is, say, the column, we don't need to change, we just change the base, the bracing pattern, then we can just change the variable, and then we got a new structure. This can help us to do a study option, right, to help the architect to see which one is the best in terms of the artistically and also in terms of structural behavior. This is another one, so it shows the double layer bell truss or single layer bell truss, etc. And one important thing is we can also, we have our own data, well, once we got the own database, right, we are not based on the BIM model. We have our own database and we have our own program to extract the data, right, from the grasshopper, from the vinyl, and then we can generate our own 2D drawing, which match whatever we define, right? Not just press a button and the BIM software give you the plan drawing, but we define what we want to show in our drawing. We can also do this by a computer design optimization, CTO, and which also with this element system defined, right, we can easily obtain the data and then help us to do an optimization study. Pushing, say, more column, what will happen? If less column, deeper beam, what is the behavior? Which one is the best for this option, etc., etc. And we can do iteration 1 very easily and to get the best result in terms of thickness or strength or whatever. Now, what I described previously is basically various procedure. I think is quite discrete in the past. And what we did is we have created this analysis and design engine. Actually, it's a software to control BIM model, to control an analysis model, and to design a other system, to link with other system. And this is a simulation for a high-rise building, and actually it's a nonlinear analysis. And you can see the base of the building. We simulate the earthquake to do a performance-based analysis. We are not using acceleration because the ground is actually shaking and not acceleration. And so that you can see the high mode effect of the building, right? How the building is changing and so forth. Now, this is a nonlinear analysis. And the model for checking performance-based design, the model are different from simple linear analysis because we are not talking about a simple linear analysis. And we have to consider the spread of plasticity of the building and how the load will spread and so on. So, but according to code of practice, we are based on what we call the linear model. Right. Now, but linear model and nonlinear model, we have, for nonlinear model, we are probably triple or maybe 4 or 5 times information we need to punch in order to do the analysis. So it means that even though we have a structure, but in terms of element cutting, right, nonlinear model may be probably far more than linear, definitely. And then we need, it means we basically need 2 teams of people, one doing a linear, one doing a nonlinear, etc. Right? So it's very time-consuming and labor-intensive. Now, what is this analysis and design engine do? Is besides general layout, plan, dimension, elevation, it can extract the data to do a linear model, create a linear model, so that we can do the linear analysis. And from the linear analysis, we can do the code check for the member sizes, right? But at the same time, it can create a nonlinear model. It can create other kind of model. And one important part is a connection. Now, this is a diagram showing the analysis and design engine. Normally, I think now in commercial world, I think we've got a BIM model. You can probably do this one and do this one. Whether you accept, depends on how the capability of the software. But at the same time, what we did is generate an elastic model. Some now BIM system saying that they can create a linear model, but I can't find anyone that can produce the same structure for nonlinear analysis. Right? So what we did is we have this engine, and then we have set up our own parameter to create a nonlinear model so that we can do nonlinear analysis. But at the same time, more important, we create a connection model which is linked to the geometry. And with the connection model, we have the brace, for example, the bracing. The bracing, we have a stiffener inside a column. And if the bracing angle change, the stiffener change. If the bracing member thickness change, the steel plate change, the stiffener inside the column change as well. And by that, we can we can extract, export a connection IGES model, and then we can do a meshing, and then we can do finite element analysis, and then got the result, right? So if the geometry change again, the connection will change automatically, and then we can repeat this process, but with the ready in-hand finite element model. This is the example we have used. And also, with that one, we also link it with the XDill detector. And so that after the analysis, if we find satisfactory, right, then we have the texture model ready with all the steel plate, with all the layout for cutting, for manufacturing. So with this one, it's very easy to facilitate, to accelerate our to increase our productivity a lot. And also, this is the real example of that mega column for Tianjin 117. The column, the building is 600 meter tall, and the column size at the base is 11.5 times 4.5 meter, pretty big. And you can see we have a multicellular, and you can see a labor and so on. This is the column. All right. And you see how we can link with the construction. At the same time, this is the Tianjin 117, and it's now above ground, and probably it is continuous building the superstructure. I hope that probably within maybe 2 years, this building could finish. And also at the same time, we use the same technology, right, for our Beijing C15 project, which is 550 meter. Right? And I think this is a good example showing that how engineer could actually control BIM model and don't let BIM to control the structural engineer. And the idea of this engine is to control other software and obtain the result that we are looking for. And at the end, we'd like to thank you, company, to give us such a research fund to develop this engine. Thank you very much.